All right, I want to give a little bit of an intro before we jump into graphing rational functions. There's a fair amount of notation here, and basically I would say just like polynomials, I wanted to put this all in one place, and I think this is something you should come back to after you've worked through some of your homework and see if all of these things make sense, if you're really checking all of these, and let me know if not. So first thing, remember that a rational function is a polynomial divided by a polynomial. And remember that polynomials can be as simple as a constant function. So like p of x could equal 2. It could just be a 2 in the numerator. And they can get as messy as quadratics or cubics or fourth degree or fifth degree and so on. So these could get really, really messy. And we want to focus a lot of in the middle, not the simplest functions that just have linear or constant numerators or denominators, but maybe quadratic and cubic and a little bit of that higher stuff. We're going to take a new approach. So in a pre-calc 1, you hopefully did some graphing transformations of 1 over x and 1 over x squared. And I will look at that in our first example just to remind you, but we want to approach this with this understanding of local behavior and global behavior. So local behavior is going to include zeros, just like with polynomials, vertical asymptotes, which do go forever vertically. They go all the way up to positive infinity for a y value and down to negative infinity for a y value. But I'm still going to call that local behavior because the x's are not going to be huge numbers. We're going to see a lot of vertical asymptotes happening at x equals 0 or x equals -3 and so on. And then the other one that we certainly did not see with polynomials is there can just be a hole in the graph. It can be going along and looking pretty normal, and then all of a sudden we'll just have a discontinuity, which you should have seen before, but not as part of any of our parent functions. So it is kind of an interesting one. Global behavior, we're going to have a few options. So for the local behavior, it could have all three of those. You could have all of those happening. For global behavior, it's going to be one of these things. So this could be any, all. This could be only one. So this will be based on potentially the degree of the numerator versus denominator. And if the degree is the same, then it will go into the leading coefficients of the numerator and the denominator. So we're not going to have both a horizontal asymptote at y equals 0 and then also a horizontal asymptote at y equals c over d, which we'll get into. And we also won't have either of those along with this last scenario where we use long division. And generally what we find when we use long division is that there's some sort of slant asymptote. So this is going to be one of these things will be our global behavior. So just like with polynomials, you could have multiple x-intercepts with different multiplicities, but you only had one function determining the global behavior. So this should boil down to basically like a checklist. So for the local behavior, you're going to ask, are there any zeros? And that would happen if the numerator equals 0, but the denominator doesn't. Are there any vertical asymptotes? And that would happen if the denominator equals 0 and the numerator doesn't. Or is there a hole in the graph, which happens when the denominator and the numerator are both equal to 0? And then for the global behavior, again, kind of a list that you just go down. It's just that you're not going to answer yes to all of these questions. You're first going to check the degree of P versus Q. And then depending on which of these three scenarios you have, you should be able to determine either a horizontal asymptote at 0, horizontal asymptote based on the coefficients of P and Q, or some sort of slant asymptote as your global behavior of R. So again, come back and look over this and see if this notation is making sense and if you're understanding all of these pieces.